In my last lecture, I have discussed on the effect of contaminations on device performance. What should be the clean room environment? What should be the clean room conditions? How much dust particle size or how many dust particle size are allowed inside a clean room? All those things I have discussed in detail. Now, today's lecture will be on wafer cleaning technology. We have to clean the wafers. Particularly here, I will discuss on silicon wafers. For silicon VLSI, the wafer or substrate used is single crystal silicon, either P-type or N-type. And those silicon wafers are properly cleaned before further processing. And what are the technology used for cleaning the silicon wafers? That will be the topic of discussion in this lecture. And you know, VLSI technology now has entered into the era of ULSI technology or ultra large scale integration technology. And present ULSI technology requires more stringent and reliable means to control the surface smoothness to get rid of particles and contaminations. And surface smoothness is a very important consideration now in VLSI technology. The reason is that the minimum feature size is going down to sub-quarter micron technology. And the metallic and organic residue size are of the order of say 0.5 or 0.6 micron in some cases. So obviously they may act as a killing defect. Organic residues on silicon wafers can damage the surface. So how to remove those those contaminations, etc., that is the subject of discussion now. The well-known RCA wet cleaning process have been used extensively since 1970s. The basic mechanisms of cleaning will be discussed in this lecture. Recent developments of cleaning process will also be discussed in detail, which will meet the more severe requirements and various applications of VLSI process or VLSI technology. Now, let me discuss on the objectives. Primary objectives of the wafer cleaning technology are a removal of particle contamination, a removal of organic contamination, a removal of metallic or ionic contamination, improvement of surface micro roughness, a removal of native oxides. Now, the particle contaminations, organic contamination, metallic or ionic contamination, how they can kill the defects, how these contaminations affect the different parameters of the devices has already been discussed in my last lecture. Now, we will just here in this lecture discuss the ways and means to remove those contaminations. All the containers in the process environment or process room should be made of quartz, Teflon or polypropylene and not glass, because glass are the sources of sodium or potassium ions, which are also defects which act as a alkali ion, and those ionic contamination will damage the properties of the oxide. Water resistivity should be between 12 to 18 megohm centimeter, and this water is known as deionized water. Normal water which we drink every day or which we use in our household, those water's resistivity is not that high, because normal water contains lot of metallic ions, lot of minerals, etc. And because of the presence of the minerals or metallic ions or atoms, the resistivity is nearly 1 kilo ohm or something like that. But if you remove all those ions, so this water is then deionized. There are certain techniques by which the ions are removed from the water, and ions should be removed in such a fashion that resistivity of water may go up to 16 to 18 megohm centimeter. So that water is suitable for cleaning purpose. In wafer cleaning process, in many subsequent intermediate steps, we need rinsing of the wafer using good quality water, and that water, good quality means it should be metal or iron free, and that is known as deionized water, and its resistivity should be 12 to 18 megohm centimeter. All reagents or chemicals used for cleaning the silicon wafers are ultra pure and ultra filtered. The chemicals grade for processing the VLSI chips are VLSI grades, and VLSI grade means there the impurities should be as minimum as possible, is ultra pure, and that grade is sometimes known as MOS grade chemicals, sometimes known as electronic grade chemicals, and sometimes it is known as semiconductor grade chemicals. And the chemicals which the chemistry students use in their laboratory for different reactions, that chemicals are known as laboratory grade chemicals, and the chemicals used in microelectronics or VLSI process lab are different from those used by chemistry researchers and students. And VLSI grade chemicals should be ultra pure as well as is ultra filtered. That means those chemicals should not be the source of dust particles or particulates. So if it is ultra filtered, then the chemicals will not be the source of particle contamination. And the electronic or semiconductor grade chemical, obviously if you use ultra pure and ultra clean, ultra filtered chemicals, it is highly expensive, and the expense is almost 10 times to 15 times than that of laboratory grade reagents or chemicals. So those are the special points which is to be noted before starting the wafer cleaning process. Now, the particle contamination, I will discuss on that particular topic little bit in detail. What are the sources of particles and how it affects. By the year 2000 or 2001, that means at present moment, 0.2 micron device feature needs particle size less than 0.02 micron. The sources of those particles are from process equipment. They may come from ambient gases, because in the process lab we use a lot of gases like high purity nitrogen, oxygen, hydrogen, argon, etc. And those gases, process gas, those are known as the process gas, and those process or ambient gases may be the source of contamination, and those gases should not contain any particles, whatever small means 0.2 micron or 0.5 micron, whatever size may be. So that's why in process equipment or in furnace, when we flow certain gases, and before sending into the furnace tube or in the process chamber, so those gases are filtered using special kind of arrangement. So these filtered gases are flown inside the process equipment. and deionized water is also a source of these particles. Now, the causes. These particles can cause less yield reduction, and gate oxide quality may deteriorate, because of which the yield will be poor. Low oxide breakdown field of the oxide will be less, and metal bridging. These are the effects. Metal bridging, etc. These are the effects of the particle contaminations. Now, how to get rid of those particle contaminations? The ways are dissolution, oxidizing degradation, lift off by slight etching of the wafer surface, and electronic repulsion between particles and wafer surfaces. So all these methods, dissolutions, oxidizing degradation, and lift off, that means first oxide formation and etching of the oxide, and by that technique also you can remove those particles. Most of those processes are used, or techniques are used in different etching methods, and those will be discussed in this lecture itself. Now I am coming to organic contamination, and the organic contamination sources are organic vapor in the ambient. You know, in the cleaning of silicon wafer, sometimes we use some organic gases, and sometimes we use organic chemicals, organic liquids also, and those organic liquids may vaporize in the ambient, and the ambient may be the source of organic contamination, and those organic contamination may affect the devices in further processing. And the causes for these organic contaminations are hydrophobic silicon surface, and at this juncture I should clarify what is meant by hydrophobic silicon surface. Silicon by itself is hydrophobic in nature, but silicon dioxide is hydrophilic in nature. That means if a surface is silicon surface is covered by silicon dioxide, and if you dip the silicon dioxide in silicon wafer along with silicon dioxide inside a beaker containing water, then you will find if you take out the silicon wafer, the water sticks on the surface. So water sticks on the surface means you can guess that on the surface of the silicon a layer of oxide thickness is present, and that is why water is sticking on the surface of the silicon. But if the silicon dioxide is etched completely and if bare silicon is coming out, and then water cannot stick on the bare silicon, and that will be hydrophobic in nature. And that natural property which has been provided by silicon and silicon dioxide has given us an opportunity to diagnose or to identify whether the silicon surface is free from any native oxide or any grown oxide. And this particular technique or this particular identity helps us for etching of silicon dioxide, for opening windows in silicon dioxide. In a photomasking, after photomasking, before the diffusion or implantation technique, when we are going to open windows in silicon, then sometimes we put a check wafer, and we can see from the check wafer whether the wafer is becoming hydrophobic or hydrophilic. As soon as from hydrophilic it becomes hydrophobic, we assume, or we can assure that the silicon dioxide has completely removed by silicon dioxide etching solution. So here in this particular point we can just see that if any of the organic contamination is present, so silicon can be hydrophobic also, and this hydrophobic nature will prevent aqueous medium from cleaning silicon surface. Any portion of the silicon wafer is covered with any sort of organic contamination, and for example fatty acid is a organic contamination, and that can come from human body. If you touch with your finger on the silicon surface, or if you catch a wafer by your bare hand, so then the impression from your finger will come on the surface of the silicon, which is the organic contamination, and that impression can prevent aqueous medium from further cleaning of the silicon wafer, silicon surface. Leaving contaminants such as native oxide or metal impurities. Micro masking effect in later RI process. So any source of organic patch on the surface, organic contamination patch on the surface will prevent the will act as a micro mask, and it will prevent from RI etching. So those are the effects of the organic contamination, and which can deteriorate further processing or further steps. Change in oxidation rate. If the surface of the silicon already contains some organic contamination patch, then they can change the oxidation rate of the silicon. Now, how to remove those organic contaminations? They can be removed by dry acing, by ozone, followed by subsequent wet cleaning in H2SO4 and H2O2 3:1 to 4:1 at 120 to 130 degree centigrade. So the H2SO4 and H2O2 mixture, so in the ratio of 3:1 to 4:1, if you prepare, then a lot of nascent hydrogen will evolve, and that will react on the surface, and all organic contaminations will be cleaned, and the temperature of the mixture will increase to 120, sometimes it is also heated to 120 to 130 degrees centigrade. Other gross removal schemes are with chromic or sulfuric acid cleaning, acetone, alcohol and DI cleaning, plasma etching. So these are the several schemes which are followed to remove organic contamination from the surface of the silicon wafer. For example, the chromic and sulfuric acid cleaning is not used in case of silicon, but it is used for cleaning quartz wares or glass wares. So the accessories or the beakers or petri dishes or some other gadgets which are used in cleaning silicon wafers, those are periodically cleaned using chromic and sulfuric acid, because those accessories, clean room accessories, may contaminate with organic patches or organic contaminations or oils or fatty acids or etc. And that has to be removed in certain interval of time. So now these are the organic contamination removals, and silicon wafers sometimes organic contamination are also used by acetone and alcohol, and then by DI water rinsing, and in dry process we can remove the contamination by plasma etching. Now I am coming to the metal or ionic contamination. In this particular case, the ionic and metallic contamination sources are from equipments, from chemicals, reactive ion etching system. It may come from implantation, and sometimes we follow a step of plasma etching. From there also the metal or ionic contamination may come. Equipments are the common source of metal or ionic contamination, because most of the equipments use some metallic frames, and from the metallic frames, which may experience different temperature, higher temperature also, from those frames or at high temperature metal, some of the metal ions or metal molecules may come. chemicals obviously be a source, and when you are implanting with certain dopant, so from the implanted machine also some other metallic or ionic contamination may enter into the substrate along with the dopant implantation. So now what are the causes? Then we will come how to remove those ionic or metal contamination. Due to the presence of metal or ionic contamination, we may face low breakdown field, junction leakage current can increase, it may reduce minority carrier lifetime, high metallic or ionic contamination may reduce the minority carrier lifetime, threshold voltage may be shifted. These are the causes of metal or ionic contamination. And a removal, how can remove the metal or ionic contamination? That is done by RCA wet cleaning process. RCA wet cleaning process is followed for quite a long time for removal of the metal or ionic contamination, and now I will discuss the RCA cleaning process little bit in detail in the next slide. So RCA wet cleaning process was first developed by Kern and Putenin at RCA laboratory, and it was published in 1970. It consists of two sequential cleaning steps known as SC1 and SC2. This process removes organic, ionic and heavy metal contamination from the silicon surface. And now we will discuss the steps of RCA cleaning process. It follows three steps. First is standard clean 1, SC1, and the SC1 or standard clean 1 test is NH4OH, H2O2 and H2O, the ammonium hydroxide, H2O2 is hydrogen peroxide, and H2O water, obviously the deionized water. Those compositions are taken in 1:1:5 to 1:2:7 ratio, and they are heated at temperature 70 to 80 degrees centigrade, and the silicon wafers are kept inside the solution for 40 minutes. So that is the step 1, standard clean 1 or SC1 step. Ammonium hydroxide is 1 part, hydrogen peroxide may be 1 to 2 part, and water may be from 5 to 7 part. This is the composition. Ammonium hydroxide in this particular composition provides solvating action. Hydrogen peroxide oxidizes to produce volatiles, and those volatiles are H2O, NH4, ammonia and oxygen. The contaminations means the heavy metals or ions or even organic. Those contaminations, some of them are dissolved in NH4OH, some of them will oxidize with in presence of hydrogen peroxide, and they will form H2O, ammonia and oxygen, and later on all those gases will be exhausted, that is they are volatiles, and they will come out of the solution. Organic contamination and some heavy metals, for example gold, are removed in this particular RCA cleaning step. And during the cleaning procedure, it forms a surface chemical oxide, which is sometimes known as native oxide, and that oxide is of the order of 15 angstrom unit. And each cleaning step, that means standard clean 1 step for example, is followed by a rinsing in deionized water. So after the wafer is rinsed with deionized water, you can see the surface is covered by a native oxide which is formed in the reaction, and that oxide is of the order of 15 angstrom. So that oxide has to be removed before the next step, and now you have to etch up the surface oxide before going to the next step, standard clean 2 step. Surface oxide, if it presents on silicon wafer, they can hinder sodium removal in the next step. A removal of thin oxide in dilute hydrofluoric acid is done in a modified RCA process. So that means if you include this step, they may call it modified RCA process. So this thin oxide which is formed in the first reaction, that is SC1, that is removed by dilute hydrofluoric acid, that required about 60-second time at room temperature. Now we are coming to standard clean 2, that is SC2. And what is SC2? SC2 clean process is, again, you have to prepare a solution with a composition of hydrochloric acid, hydrogen peroxide and water, and here the compositions are 1:1:6 to 1:2:8, means 1 part HCl, 1 to 2 part hydrogen peroxide, and 6 to 8 part is water. So all these mixtures are taken in a beaker and it is heated at a temperature of 70 to 80 degrees centigrade, and the wafers are kept inside that beaker or immersed inside the solution at temperature which is maintained at temperature 70 to 80 degrees centigrade for 20 minutes. So that step is known as standard clean 2 step. In this particular reaction, the HCl provides chlorine complexing to remove inorganic ion contamination. So what is chlorine complexing? The HCl will react with ionic or atomic atom, that is gold. For example, gold with HCl, it will form gold chloride, or copper atom with HCl, it will form copper chloride, and sodium will form sodium chloride, etc. So those chlorides contaminate, that is the chlorine, those chloride, the chlorine complexing will help us to remove this metallic or ionic contamination, because those are dissolvable in the solution. So now solution means dissolvable in water. This particular step also yield a thin chemical oxide which is of the order of 15 angstrom thickness, and this chemical oxide also removed by dilute hydrofluoric acid dip. So that means the total process RCA process is a combination of 3 steps. First step is known as SC1, standard clean 1. Next is the removal of the native oxide, and the third one is standard clean 2, SC2 step. And SC1 step we use ammonium hydroxide, hydrogen peroxide, water, and SC2 step we use HCl, which is hydrochloric acid, hydrogen peroxide H2O2, and water. So the combination of these 3 is known as modified RCA process. Recommended cleaning procedure of silicon wafers is as follows. First we go for Pirhana clean. Pirhana clean is also known as the Karos acid cleaning. What is Karos acid? That is mixture of H2SO4 and H2O2 in the ratio of 1:1. That means 1 part concentrated H2SO4 means sulfuric acid, 1 part concentrated sulfuric acid and 1 part hydrogen peroxide. If you mix, then that is known as a Karos acid. So that Karos acid will clean silicon surface, that will remove the organic contaminations at the beginning, and that is very helpful and is known as Pirhana clean. And after Pirhana clean, we can rinse the silicon wafer by step which is known as overflow rinse. Then comes SC1, which is overflow rinse. SC1 then comes, SC1 is not overflow rinse, sorry. SC1 is the ammonia solution H2O2 and H2O clean. Then overflow rinse. Then HF dip. This HF dip will etch off surface oxide. Then comes again overflow rinse. Then SC2. SC2 is HCl, H2O2 and H2O clean. And then again overflow rinse. Then spin dry. So after each step we use water rinsing, that is DI water rinsing, which is known as overflow rinse. At the end, we dry the silicon wafers using some spinning technique, and that is known as spin dry technique. Now, surface micro roughness. An important issue in fabrication of high performance and high reliability submicron and deep submicron VLSI is to remove micro roughness. In the year 2000 and beyond, 0.1 micron technology, the thickness of gate oxide has gone down to 40 angstrom, means 4 nanometer only. Surface requirement should be atomic flatness. So that's why the surface of the silicon should be mirror finished or atomic finished. Sources of those roughness are from initial wafer material, standard chemical process, because standard chemical process, it can etch little bit from the surface and that will produce certain roughness, and those roughness will hinder in subsequent process, means subsequent metal interconnect or contact problems you may face if surface roughness is extremely high. And sources of these micro roughness, as I mentioned, then causes micro roughness can lead to low oxide breakdown field, low mobility of carriers. Here the RCA clean also produces some micro roughness. Standard clean SC1, which is NH4OH, H2O2 and H2O, 1:1:5 at 70 degrees centigrade for 40 minutes, they results in a rough surface due to the oxidation by H2O2 and etching of the oxide by NH4OH. So surface etching may lead to some kind of roughness. In SC1 cleaning technique, the hydrogen peroxide, they oxidize and oxidize silicon, and that oxide is etched by ammonia solution, which produces some kind of roughness. Now, a remedy for this particular roughness formation is as follows: reduce the proportion of NH4OH. Second is reduce the temperature of the bath. Third remedy is reduce the cleaning time. And here in this particular picture, you can see the roughness values. SC1, this is this curve here. SC1 is micro roughness is such that the wafer has some ups and downs from 2.2 nanometer, means 2 angstrom to 6 angstrom. That means 4 angstrom unit variation roughness is seen in case of the SC1 cleaning. And now, as I mentioned, the roughness may be reduced to the level of SC2 cleaning. SC2 cleaning produces a roughness of the order of say only 2 nanometer, 2 angstrom, 0.2 nanometer. Okay. And here the SPM is SO4 H2O2 cleaning. That is basically the Piranha or Karos acid cleaning. There also produces roughness of the order of 2 angstrom. And the control means if you HCl, H2O2 and H2O cleaning, so that is SC2 cleaning, and control amount of NH4OH you use, that means if you reduce the ratio of NH4OH from 1 to 0.5, then the roughness will also reduce. It is of the order of SC2 process, you can see here. But if you reduce the NH4OH by half, that means from 1 part to 0. 1 part, not half, even less than that, from 1 part to 0.05 part, then the efficiency of particles and metal impurity removal is reduced due to increase of NH4OH, due to decrease of NH4OH ratio. So NH4OH basically removes the particles, but if you reduce its amount into the solution, then it also loses its efficiency for particle removal. and optimization is thus highly desirable. Now, native oxide. Native oxide is an important issue in advanced VLSI process, because if your native oxide is of the order of 2 or 3 or 4 angstrom unit, so then a recent gate oxide is nearly 40 angstrom. So 40 angstrom there, if 20% or 10%, 15% variation, then oxide thickness will not be uniform, and there is a variation of device performance because of different threshold voltage due to the non-uniform thickness of silicon dioxide. And if you keep an wafer 7 days in a clean room air containing 1.2% H2O, the thickness of native oxide is about 6 to 7 angstrom. You see, it's not small. 6 to 7 angstrom native oxide will form if you keep a bare silicon wafer in a clean room for about 7 days. The sources of the native oxide, how it is formed, that is because of ambient moisture, DI water rinse, and it causes, this native oxide causes uncontrollable ultra thin gate oxide. It also degrades gate oxide. It also causes low quality of epi layer. It inhibits selective growth of CVD or epitaxy. Native oxide offers a high contact resistance, poor silicide formation. And another cause of native oxide is the source of metallic impurities which diffuse or precipitate at the silicon dioxide interface and cause defects in succeeding high temperature process. So these are the various causes of native oxide. Now, how to remove those native oxides? A remedy is like this: nitrogen gas bubbling, which reduces the partial pressure of oxygen in water. Theoretically, oxygen pressure can be reduced to less than 0.1 parts per billion with this method. What is nitrogen gas bubbling? That means the water which you are using for cleaning the silicon wafer, in those water container, continuously nitrogen is bubbled. If you continuously bubble nitrogen, high purity nitrogen into that water, then the dissolved oxygen inside the water will go down. The partial pressure of the oxygen will reduce drastically, and that will help in removing the native oxide formation problem. So that is one remedy. And another is degassing in a membrane module. By that technique also you can you can get rid of the formation of native oxide. Now I will discuss some of the advanced cleaning process, and those advanced cleaning process are required in certain steps. One is a low temperature cleaning process. At this particular cleaning step, this particular cleaning process is given by Japanese scientist Shiraki. That's why it is now known as Shiraki clean process. Now, why this particular low temperature cleaning process is coming? You know, if you want to form epitaxial film on silicon, which is an essential layer for making devices either in bipolar on or MOS devices, so those epitaxy are formed in ultra high vacuum, in very high vacuum ambient, and at high temperature, and that temperature is in the range of 1100 degrees centigrade or 1150 degrees centigrade. Now, in all epitaxial process, first step is the removal of native oxide, and that native oxide is removed inside the chamber, and the chamber is kept at a very high temperature, and those oxides, means native oxides, inside the epitaxial chamber are removed by sintering the wafer at very high temperature, and that temperature is nearly 1100 degree centigrade. And it has been observed after removal after cleaning of the silicon wafer, if you take the OJ spectroscopy, then you will find on the surface of that clean silicon wafer, you will find traces of contamination of carbon. If the traces of contamination of carbon is there, then if you go on depositing silicon crystal, epitaxial silicon crystal, then the quality of the silicon crystal will be bad, and that crystal cannot be used for further fabrication of VLSI chips. So you have to remove those carbon contamination which is present inside the native oxide. In order to remove all those contamination, the native oxide is removed at a very high temperature of the order of 1200 degrees centigrade, and that high temperature, if we clean or if you remove the native oxide, then the problem is the redistribution of impurity. Before epitaxial formation, already buried layer implantation has been done, and the buried layer impurities will outdiffuse vertically as well as laterally, and because of that impurity redistribution, the lot of silicon, bulk silicon will be consumed, and that is why we need a low temperature cleaning process. And here the cleaning means removal of native oxide process, so that the redistribution of the impurity before epitaxial growth is prohibited. And in that particular process, we follow first degreasing and then night HNO3 boiling. The silicon wafer is degreased first, then we boil it in nitric acid and dilute hydrofluoric acid, that is 2.5% dilute. And the third step is NH4OH, H2O2 and H2O, 1:1:3, that is a standard clean 1 step, followed by dilute hydrofluoric acid dip, that is for removal of the native oxide. Next comes HCl, H2O2 and H2O, 3:1:1, that is standard clean 2 step, and rinse and spin dry till become uniform hydrophilic. This is basically the Sirachi clean process. If you follow this process, then the native oxide in epitaxial reactor can be removed at 800 degrees centigrade, and after 800 degrees centigrade sintering before epitaxial growth, the surface is again examined by OJ spectroscopy, and we have seen that no trace of carbon or other oxygen contamination is available after sintering it at 800 degrees centigrade. So that is suggested by Sirachi and is followed in many steps before, in many cases before epitaxial growth. And another wet cleaning process is given by OMI, and that is H2O3, that is O3 is ozone H2O, which removes organic contamination. Then NH4OH, H2O2 and H2O, that is in the ratio of 0.515, particle organic and impurity metals are removed by that. Next step is hydrofluoric acid 0.5%, H2O2 10%, native oxide and metallic impurities will be removed in this particular step, and the last is ultra pure water rinsing. These 4 steps combinedly known as the OMI cleaning process. Now another advanced cleaning technique is IMC, which is known as Inter-University Microelectronics Center, IMEC. The IMEC cleaning step is shown in this particular diagram. Here the IMEC cleaning is a combination of 4 steps: step 1, step 2, step 3 and step 4. Step 1 is oxide growth, and that is about 1.5 nanometer of chemical oxide. In a step 2, we remove that oxide removal by either dry hydrofluoric acid or hydrofluoric acid vapor and rinsing. And the step 3 is optional. Then again you can form a chemical oxide, and step 4 is the drying. So either step 1, 2 and this 4th step may give you the IMEC cleaning, or the optional step which is step 3, that also you can use. So this combination of the 4th step is known as the IMEC cleaning step. So now the yield is one parameter which will define how the wafers are cleaned from the contamination. So that is basically basically known from the breakdown field. The yield is equal to percentage of gate oxide with a breakdown field larger than 12 megavolt per centimeter. Now, if you compare in the next slide the different steps, the breakdown fields, then you can see IMC plus RCA spray, that will plus HF bath will give you 80% yield, and IMC clean plus RCA spray will give you 65% yield, and RCA bath will give you 60% yield. IMC bath will give you 83% yield. So now IMC gives 83% means it is better. Now another method is a dry cleaning technology. Dry cleaning technology here is very important. Although wet cleaning technology still remains the major methods for wafer cleaning, VLSI industry has begun to recognize problems associated with wet cleaning. Among different problems in wet cleaning process, some are the particle generation, drying difficulties, cost, chemical waste disposals, incompatibility with advanced concepts in integrated processing, and general inflexibility. The dry cleaning process may provide a way to solve these problems, although currently it is not completely useful. The dry cleaning process, a kind of gas phase chemistry is used. It requires this particular gas phase chemistry for excitation energy, which will enhance the chemical reaction at low temperature. This added energy may be plasma, this added energy may be particle beam, short wavelength radiation, or thermal heating, which enhances the surface cleaning result but must avoid the side effects of damage to the wafer. Recently, many dry cleaning processes have been developed, which are hydrofluoric acid H2O vapor cleaning, ultraviolet ozone cleaning, hydrogen argon plasma cleaning, and thermal cleaning. Thermal cleaning, here removal of native oxide by heating the wafer to 800 degrees centigrade ultra high vacuum, which I discussed in earlier slides, that is Siraki clean step. Now I will discuss in this particular class the dry cleaning technique, and that dry cleaning technique is ultraviolet ozone clean or UVOC cleaning technique, and that cleaning technique is shown in this particular diagram, that is ultraviolet ozone cleaning. This is a very effective way to remove hydrocarbons, although the surface is oxide passivated. The mechanism of UVOC or ultraviolet ozone cleaning can be explained by the following process equations, and which is given here. The absorbed impurity plus H nu is the ultraviolet radiation, and when the ultraviolet radiation whose wavelength is 200 to 300 nanometer and that is absorbed, then they are excited and ionic impurities will be formed. And now this oxygen is again absorbed by H nu, is 185 nanometer ultraviolet light, and that will give you 2 oxygen. This is oxygen molecule and it is giving atomic oxygen. This atomic oxygen again react with oxygen molecule at 254 nanometer wavelength and it forms ozone. This ozone atom plus H nu, again it can go back to oxygen atom and oxygen molecule. Now the ionized impurity, that ionized impurity is coming after absorption of the ultraviolet ray of 200 to 300 nanometer wavelength. Now this impurity atom along with the ozone and oxygen, they are volatile. This impurity means ionized impurity. The ionized impurity and oxygen and ozone, they are volatile, so they can be removed easily from the surface. So this is a very important step. The reactions here is a basically surface excitation. Surface excitation reaction is here, where the absorbed impurity formed the excited or ionized impurity with the help of the ultraviolet ozone. And gas phase reactions are these reactions that converts impurities such as hydrocarbons into volatile gases, and those volatile gases can be ejected from the environment. So here we have not used any sort of these wet chemicals. All are the either radiations or some gases, and it has got advantage nowadays in case of cluster processing. But now in a recent modernized VLSI techniques, many steps are integrated together, and which are known as the cluster processing. And in cluster processing technology, always we use these dry processing. So I hope by this time you have understood the importance of wafer cleaning process, and starting from the RCA wafer cleaning, I have discussed many of the advanced cleaning steps also, and at the same time I have addressed some of the recent dry processing, dry wafer cleaning steps, which is very important in modern clustered or integrated VLSI process. Thank you.
We will now show you how silicon wafers are cleaned using Karos acid. Karos acid is a 1:1 mixture of sulfuric acid and hydrogen peroxide. He has first poured the hydrogen peroxide Now he is pouring sulfuric acid into the beaker. Notice that when sulfuric acid is poured, a vigorous reaction occurs. Nascent hydrogen is released in the reaction that helps to free the wafer from inorganic contaminants. The wafer is kept in the beaker for about 8 to 10 minutes. By this time, the reaction slows down. The wafer is now taken out and dipped in DI water for rinsing. Please notice that the wafer is being dipped in a series of beakers containing DI water. Subsequently, this wafer would be taken out and dried in a spin dryer.